So I have a couple questions for you. Based on these equations, what is the relationship between wavelength and frequency? So C equals wavelength times frequency, speed of light. Second question is, what is the relationship between energy and frequency? See that here? And then how could you write energy in terms of wavelength? So take a moment, see if you can answer these questions, and then I'll talk about them. Okay, so the relationship between wavelength and frequency. If we think about it, right, it's going to be inverse because they have to equal C. They always have to equal the same value, which doesn't change. So if wavelength goes up, in order to keep this the same, frequency will need to go down, right? When we think about the relationship between energy and frequency, right, this has to stay the same. So if we solve for Planck's constant, it would be Planck's constant equals energy divided by frequency, and it always has to be the same. So as energy goes up, frequency would also have to go up, so they are proportional to each other. So that means more frequency equals more energy. That also means less wavelength equals more energy, because these are inversely related. And if we wanted to write energy in terms of wavelength, we could do this, right? If we solve this equation for frequency, we get frequency equals the speed of light divided by lambda, the wavelength. We can plug that in for F down here. And we have energy equals Planck's constant times the speed of light divided by our wavelength. All right, we'll practice with these equations a little bit. And I will be there next week. I don't know if I mentioned that, but then we'll do some practice with that stuff. So here's a quick check. What do we call this region to the right? So this one over here, right? What is this region called in the electromagnetic spectrum? What do the letters stand for? Right? And then which color of visible light has the longest wavelength, the highest frequency, and the greatest energy? So see if you can answer these. Take a second, and then I will tell you the answers. So this is the visible light part of the electromagnetic spectrum. This is what our eyes can see. It is a very, very small part of the spectrum. Fun fact, some animals can see into the UV part. Some animals can see into the infrared part, which is kind of cool. The letters stand for different colors, right? Red, orange, yellow, green, blue, indigo, violet. And the color of visible light that has the longest wavelength would be red, right? It is the biggest number over here. The highest frequency would be violet, right? Because as wavelength goes down, frequency goes up. And the higher the frequency, the higher the energy. So violet is also the greatest energy, which means ultraviolet, which is on this side, has even greater energy, and infrared has even less energy than visible. So here's some more questions. Identify the region of the electromagnetic spectrum that has the shortest wavelength, the lowest frequency, and the lowest energy. So take a second, try and answer those questions. Okay, so the region that has the shortest wavelength, that is going to be gamma rays. That's what this symbol means, is gamma. Right, so super tiny numbers over here, wavelengths, as the smallest wavelengths. The lowest frequency would be the place with the highest wavelengths. So radio waves have the lowest frequency. And the lower the frequency, the lower the energy. So radio waves are also the lowest energy of any electromagnetic waves, right? So I'm going to show you this video real quick. It's super quick. And then we're going to talk about it. But this was an experiment that happened in 2011. Scientists reported a measurement that showed a neutrino particle moving faster than the speed of light. Einstein says that is not possible, right? The speed of light is constant and nothing can be accelerated past it. So this is impossible according to the laws of physics. So watch this video, listen to what they're saying, and then we'll talk about what happened next.
Yes, we found an anomaly. We found that this speed is not what you would expect, namely very close to the speed of light, but it seems to be a little higher, 20 parts per million. You could say it's peanuts, but it's not. It's something that we can measure rather accurately with a small uncertainty, because everybody knows that speed limit is c, the speed of light. And if you find some matter particle as a neutrino going faster than light, this is something which immediately shocks everybody, including us. I don't want to call this discovery. I want to say that this is a measurement. It's an intriguing measurement, it's a precise measurement, and in order to this measure to become a discovery, we will need more work. Our work and the work of the colleagues. I think our duty as Opera Collaboration, we want to get more confidence in our results, so we will continue our studies, and we will wait patiently for the confirmation. If confirmation comes, we will meet again.
So he was a spokesperson for Opera, which was the lab that made this measurement, right? And you could see he's kind of excited about it. Obviously, this would be a crazy discovery if something is moving faster than the speed of light, because we currently think that's impossible. But he was not calling it a discovery, he was calling it a measurement, and that was a good caution, because in science, one experiment does not create I should say this way. One experiment does not prove anything. You have to be able to replicate the experiment over and over again. We need lots of data to support our theories, right? So he was talking about other people working on this and supporting this theory. So basically, this experiment would need to be replicated by other labs. Unfortunately, other labs could not replicate this. People tried in other particle accelerators, and none of them could get a neutrino to go faster than the speed of light. And eventually, an experimental error was discovered in their method, which accounted for their measurement. So it turns out they did not actually see a neutrino moving faster than the speed of light. They just thought they did. But that is the scientific method at work, right? You design your experiment to test a question, you get results, you interpret them, and then you send out that to your peers, to other scientists, and that's basically a question to them that says, hey, you try and do this. Let's see if this is actually true. You replicate this. And sometimes you get an exciting measurement that turns out to not be true, and that's all right. That's part of science. So with all that in mind, you now have an assignment where you are going to look at the different parts of the electromagnetic spectrum. And there are lots of parts. So I want you to pick 3. So I'm going to go back for a second, right? Pick 3 of these different parts. I would say don't pick visible. Pick one you're less familiar with. And you are going to do a little bit of research and answer some questions. As you do your research, keep in mind there are many things on the internet, right? Some people have very interesting ideas about some of these parts of the electromagnetic spectrum that are not necessarily true or supported by any scientific evidence. So try and find scientifically valid sources as you do this research. I would like you to write down the websites where you find your information. This is not like a test or anything. This is just learning how to find good scientific information online. But you're going to choose 3 of these. You're going to answer some questions about like their uses and their dangers to people and stuff like that. And then tomorrow we'll talk about electrons and light a little bit more. And next week I'll be there and we'll keep on talking about electrons. All right. Have a great day. Bye.